Hello students, good time to all. I am Chandan Pradhan. Welcome to the channel Chandan Physics. In this video, we are going to discuss another application of Gauss law, that is electric field due to uniformly charged sphere, that is solid sphere. Let's begin. Let we consider a uniformly charged sphere of radius capital R at center O. Let charge Q is uniformly distributed on that of surface. Now we have to calculate the electric field due to that charge sphere will be spherically symmetric and radially outwards. Let we take a point P. That point is either outside or inside or on that of surface. There are three possible cases, and each possible case we found out the electric field due to that uniformly charged sphere. So here case number 1, when a point lies that point P outside the sphere, let the point P lies at a distance small r from the center O outside that charged sphere, and draw a sphere of radius r and center O, which is treated as a Gaussian surface, and the Gaussian surface the point P that lie on that of Gaussian surface, and here we take a small area element ds around that point P. Since the electric field intensity is radially outwards, that is the direction of electric field intensity E, and also the direction of ds vector, the surface area, these two are parallel with each other. Here we define a term, that is volume charge density, as we taking into consideration the solid sphere. So we have to introduce a term, that is volume charge density of that sphere. Rho be the volume charge density of the sphere, which is equal to charge per unit volume, charge Q divided by the unit volume of that of spherical cell or that of solid sphere, that is 4 by 3 pi RQ, R be the radius, pi RQ. Therefore the charge, the amount of charge in terms of volume charge density, 4 by 3 pi RQ rho, the amount of charge of that solid sphere. Since the electric field intensity E at every point of that of Gaussian surface is directed radially outwards, therefore both electric field intensity E and ds vector at point P will be in the same direction, means E vector is parallel with ds vector. Now applying Gauss law to calculate the total electric flux passing through that of Gaussian surface. Here, according to Gauss law, total electric flux passing through the Gaussian surface is phi is equal to closed surface integration E dot ds, which is equal to q divided by epsilon naught, or closed curve integration over S E dot ds is equal to q divided by epsilon naught. Here E vector is parallel with ds vector, that is theta will be 0 degree here. So cos theta E dot ds means E ds cos 0 degree, cos 0 degree is equal to 1, that is E ds. So the values written like this, that is E ds q divided by epsilon naught, or E constant to that of outside, closed curve integration over S ds is equal to q divided by epsilon naught. Here the total surface area, that is 4 pi r square, E into 4 pi r square q divided by epsilon naught, or E is equal to 1 by 4 pi r square q divided by epsilon naught. Now we put the value of q as we get here, that is 4 by 3 pi r q rho in terms of volume charge density. E is equal to 1 by 4 pi epsilon naught 4 pi r q rho divided by 3 r square. On simplification, we have rho divided by 3 epsilon naught, 4 pi cancel out, r q divided by r square. That is the electric field intensity at point P, which is outside that solid sphere having charge q. Okay. Again case number 2, when that point P lie on the surface, on the charged sphere. So case number 2, when point P lies on the surface of charged sphere. Let the point P lie on the surface of that of charged sphere. Now we have to draw a sphere of radius r and center O as the Gaussian surface. That surface is also treated as the Gaussian surface. In this case, the Gaussian surface passing through that point P will coincide with that of charged sphere. That charged sphere nothing, that is the Gaussian surface. In that case, r is equal to small r is equal to capital R. We have to apply the Gauss law to calculate the total electric flux. According to Gauss law, the total electric flux passing through the Gaussian surface phi is equal to closed surface integration over S E dot ds is equal to q divided by epsilon naught. Since E and ds vector are parallel, so we have to take closed curve integration over S E dot ds is equal to q by epsilon naught. E vector is parallel with ds vector, that is E dot ds is equal to E ds cos 0 degree is equal to E ds, or closed curve integration over S E ds is equal to q divided by epsilon naught, or constant e to that of outside integration over S ds is equal to q divided by epsilon naught, or total surface area, that is 4 pi r square E into 4 pi capital R square q divided by epsilon naught, or E is equal to 1 by 4 pi r square q divided by epsilon naught. Now we have to introduce the value of q in terms of surface charge density. So E is equal to 1 by 4 pi epsilon naught into 4 pi r q rho divided by 3 r square. Under cancellation, we have E is equal to r into rho divided by 3 into epsilon naught. That is the expression for electrical intensity at point that lie on the surface of that charge sphere. Again, case number 3, when that point lie within that of charge sphere, charge surface, that is case number 3. When point P lies inside the sphere, this is the charge sphere having center O, here is the radius r. Let the point P that lies at a distance of small r, inside that spherical shell, we have to draw the sphere having the radius small r with the center P, and that sphere is treated as the Gaussian surface which is passing through that of point P. This is the Gaussian surface here, that is the Gaussian surface passing through that of point P, and here we take the area element ds around that point P, and the electric field intensity direction is that, and that direction is also parallel to the direction of ds vector, that is the area element. The area element and electric field intensity are in same direction, since the electric field intensity is radially outwards throughout that of Gaussian surface. Now, in that of case, small r is less than capital R. Let here q dash, let q dash is the charge enclosed by that of Gaussian surface, is the charge enclosed by the Gaussian surface. Q dash amount of charge is enclosed within that of Gaussian surface. Since it is the solid sphere, there will be some charge, but in case of hollow sphere, there will be no such charge inside that of hollow sphere or spherical set, but here there will be the existence of charge. Therefore, we treat let q dash amount of charge is enclosed within that of Gaussian surface. Then according to Gauss law, the total electric flux passing through the Gaussian surface is phi is equal to closed surface integration over S E dot ds. E and ds are parallel. Here E vector is parallel with ds vector, that is theta is equal to 0 degree. The angle between E and ds, that is theta is equal to 0 degree. Therefore, E dot ds is equal to E ds, cos 0 is equal to 1. That value is written like this: closed curve integration over S E ds is equal to q dash divided by epsilon naught. Okay. Therefore, closed curve integration over S E dot ds is equal to q dash divided by epsilon naught, e to that of outside. Closed curve integration over S ds is equal to q dash divided by epsilon naught, or E, that is closed surface total surface area 4 pi r square is equal to q dash divided by epsilon naught, or E is equal to 1 by 4 pi r square into q dash divided by epsilon naught. Since q dash is the charge enclosed within that of Gaussian surface, so what amount of charge enclosed here? That is surface charge density into volume, that is surface charge density into volume. Means surface charge density means the amount of charge per unit volume, how much amount of charge within that of unit volume, that can be surface, sorry, that is the volume charge density, that is the volume charge density, how much of charge within that of unit volume into the volume of cell, means the total charge enclosed within that of Gaussian surface. Here the volume charge density is equal to q divided by 4 by 3 pi r q into volume of that of spherical cell, that is 4 by 3 pi r q. finally q dash is equal to, that is 4 by 3 pi, 4 by 3 pi cancel out, that is q rq divided by rq, the value of q dash is put here. So E is equal to 1 by 4 pi r square, in place of q dash we substitute, that is q rq divided by epsilon naught rq. Under simplification we have E is equal to 1 by 4 pi epsilon naught q r divided by rq. Again put the value of q here, or E is equal to 1 by 4 pi epsilon naught, in place of q we substitute, that is 4 by 3 pi rq rho into r divided by rq. Again simplification we have E is equal to 1 by 4 pi epsilon naught 4 pi rq rho r divided by 3 rq, or E is equal to 4 pi cancel out, rq cancel out, there will be rho r divided by 3 epsilon naught. That is the expression for electric field intensity when that point P lies inside that of sphere. So the electric field intensity inside the charged sphere is proportional to the distance r. Here the distance r, rho into r, and maximum at the surface of that of sphere, and varies inversely proportional to the square of a distance accordingly. So that can be explained with the help of the graph. If we plot the graph between electric field intensity along y axis and distance along x axis, then the graph looks like this. At r, capital R, that will be at maximum point and gradually increases below that of r, means inside that of surface, when here E is directly proportional to r. At that peak it will be gradually decreases, inversely proportional to 1 by r square. With the help of that graph we can conclude how electric field intensity varies with the distance. There are 3 possible cases we have to discuss. Electric field due to uniformly charged sphere, case number 1, when that point lie outside that of sphere, that is the expression. Case number 2, when that of point lie on that of surface, that is the expression. And finally when that point lie within that of surface, that is the mathematical expression. And with the help of that graph we conclude how electric field intensity varies according to the distance in the 3 possible cases. So with this useful and informative notes, let me wind up this session. Thank you.